Hi all, my name is Laura Seltniks, and today we're going to be discussing coastal inlet dynamics, land use changes, and land area changes in the vicinity of Oregon Inlet, North Carolina. Just a quick note, the following slides have citations noted in the bottom right-hand corner, and the reference list is available on the last slide. Okay, let's get started. So my research question was this: how can GIS be used to observe land use change, land area changes, and inlet dynamics over time in Oregon Inlet, North Carolina? And how can GIS be used to show how those changes may impact the area? I chose this topic because I'm curious about finding a balance between human infrastructure and environmental geography and human environmental interaction in coastal areas that are very dynamic. And how can we use past observations to prepare for future changes caused by environmental and human pressure? And is there a way to balance the natural processes of dynamic inlets in a way that maintains accessibility via existing infrastructure? So here's a little bit of background about Oregon Inlet. Oregon Inlet was created by a major hurricane in September 1846. A boat that weathered the hurricane was the first to report the new inlet had been opened, and that was named the Oregon, so the inlet is named after that vessel. Oregon Inlet is extremely dynamic and has migrated over 2 miles to the south since it was created, as you can see in the map to the left. There are a lot of dynamic inlets along the North Carolina coast. The map on the right shows other historical inlets. Oregon Inlet is the only ocean inlet for northern Dare County, and economic impact reports have credited the inlet for bringing nearly $1 billion to the area's economy per year. So there's a lot of public and private interest in maintaining the inlet for safety, connectivity, and economic reasons. But maintaining this inlet is tricky. It was created by a hurricane. It could definitely be closed by a hurricane. Like I mentioned earlier, Oregon Inlet gets a lot of attention because it's one of very few ocean inlets in the Outer Banks and the only inlet in northern Dare County. Getting through and over the inlet is important for visitors and residents. Search and rescue missions and Coast Guard vessels use the inlet, and the viability of it is very important during hurricane evacuations and after hurricane impact. As the land use, land area, and shoreline change near Oregon Inlet, things can get kind of complicated. Dare County has about 37,000 year-round residents, but the population explodes in peak season. In summer months, there are often 10 visitors for every 1 permanent resident in the area. About a third of jobs in Dare County are tourism-related. A 2014 report published by Dare County examined the economic impact of 5 major sectors directly tied to the navigability of Oregon Inlet, including commercial fishing, seafood, boating, recreational fishing and tourism, and tournament fishing. Maintaining the current inlet as it is today, which is a bit unreliable but mostly navigable with occasional emergency dredging, contributes about $400 million to the local economy annually. If conditions were improved or the shoreline and inlet were more stable, that contribution would increase. Likewise, if the inlet closed, the contribution would decrease. This report was published by Dare County, so it's important to note that they're very invested in keeping the inlet open, seeing as this money directly impacts the area and provides funding for other county government projects. Here's a quick overview of the methods I used to assess land use change, land area change, and inlet dynamics. I used ArcPro imagery analysis to compare Landsat 7 and Landsat 8 images from the years 2000 and 2020, respectively. For land area changes, I also found it helpful to do an NDVI, normalized difference vegetation index calculation. For inlet dynamics and shoreline analysis near Oregon Inlet, I used a USGS tool called Digital Shoreline Analysis System, DSAS, in ArcMap. As you can see, there was some overlap of methods, and the data sources were all pretty consistent. I used Landsat imagery obtained via Earth Explorer and USGS, and the DSAS tool is also from USGS. I used ArcPro to perform unsupervised imagery classification on Landsat 7 and Landsat 8 imagery. The optimal number of classes for this particular study area was 5 broad classes. The legend is shown to the right. The unsupervised classification was not very good at picking up developed areas. My research showed that Dare County's increase in population has mostly occurred in the area north of Oregon Inlet, which may have increased developed area north of the inlet, but I didn't really see that in this classification. Fortunately, the supervised land classification did a better job of identifying developed areas. It required training sites and a little bit of trial and error, but eventually I got it to work. The 5 main classes of land area are outlined in the legend to the right. Water was excluded from this classification. There were some areas, despite extensive reclassification, that had some obvious errors, especially in the 2020 analysis. Standing water in Pea Island National Wildlife Refuge might be contributing to that sort of gap in data, but the 2020 supervised classification did capture the new bridge across the inlet. I thought I would see more developed areas, especially in the area north of the inlet. Development might be slowing. After I did some research, construction permits for single-family homes issued by the county dropped 80% between 2002 and 2008. It does hint that the island is simply getting a bit crowded, and there's not a lot of room for new development of single-family homes. I was not able to find imagery that worked well with a before and after analysis of a hurricane, but I would hypothesize that other parts of the study area would see more wetlands or flooded areas near landmass edges. I excluded the forest changes from this summary on the slide. This study area was a bit small and didn't have significant forest coverage. The land loss from the supervised areas will be discussed in a couple of slides, but I think it's due to the water bodies in Pea Island, like I said before. The unsupervised classification seems to work very well for this area, I think because it's both marine and terrestrial. I think the most striking way to see land loss was just by glancing at the data. There's definitely less land in the inlet in the 2020 image than there was in the 2000 image. It was a matter of quantifying that loss with a combination of methods. Here's a false color band combination to really highlight land-water interface. The band combinations are a bit different because the left is Landsat 7 and the image on the right is Landsat 8. In addition to the land use change calculations, the NDVI analysis also shed some light on area changes in the study area. I used supervised and unsupervised classification results shown on the previous slides and the NDVI change detection difference calculation. The map on the far right shows the same study area as previous slides, just with the NDVI changes highlighted in pink. As predicted, and as you can see with just a cursory glance at the images, there was definitely a loss in total land area. Within the study area shown on the previous slides, it's safe to say that at least 9.7 acres were lost, and the unsupervised result of 12.8 acres also seems pretty accurate. Like I said, supervised finding was a bit misleading because Pea Island National Wildlife Refuge has so much standing water on it. I did also find that the census data for 2010 compared to 2020 showed a decrease in area of about 0.2 square miles for the entire county. For the scale at which this analysis was performed and the methods by which land loss was calculated, it's a bit too soon to say whether or not sea level rise contributed to land loss, but it likely did contribute to some of the land use changes, like I talked about in previous slides. I think most of this land loss was due to erosion, which could have been accelerated by storms and hurricanes in the area. I'll show a map in a few slides that shows named hurricane paths in this area. This part of the analysis was really cool. I wanted to look at how the shoreline had changed near the inlet. I downloaded the DSAS tool and used ArcMap for this part. I got some historical North Carolina shoreline data, including historical shoreline shapefiles dating back to 1849, and a baseline file that had been used by other USGS analysis in the area. I exported the shoreline files of interest for my analysis and maintained those data attributes. I added more shorelines by digitizing the lines based on Landsat images from 2000 and 2020, the same ones we've looked at in previous slides, but I also added 2 additional images from 2016 and 2021. I used different band combinations to better delineate water from land. Once I had a full data set, I used the DSAS tool to run statistics on the shoreline. The outputs included quantitative rates of change and total distances of shoreline change. This is a very colorful shoreline map for DSAS again. Only the dashed lines were used in this analysis, but I wanted to show you all the lines, dashed and solid, so you can see how much the shoreline has changed since the 1840s. The results map on the right are scaled and clipped to the years I included in my study, so 1980 to 2021. Red transect lines show areas of erosion, blue transect lines shows areas of accretion. I chose to look at one distance measurement, net shoreline movement, and one rate, the linear regression rate. Net shoreline movement shows the total distance to date that the shoreline has moved since 1980 at any given point, and linear regression rate is the rate of change in meters per year. So it shows the trend, but not the actual erosion. Average shoreline movement for this area was 41.4 meters of shoreline retreat erosion at any point, and the average linear regression rate of retreat erosion was 2 meters per year. Again, but there were areas of erosion and accretion, so material was moved and it was deposited. So we'll take a look at my original question and try to answer it. For land use change, we were able to see and quantify changes in land use cover in the study area. The patterns of change were a bit unexpected in some cases, but there are reasonable explanations for these anomalies. Land area change, we were able to see and quantify land loss in the study area by the inlet. Inlet dynamics, we were able to calculate how much of the shoreline near the inlet has changed, where it has eroded over time, and where material has been deposited. And we're also able to find distances and rates of both accretion and erosion along the shoreline near the inlet. So this analysis really only scratched the surface of what you could use GIS to study when it comes to coastal inlets. A few jumping off points for future research and analysis include hurricanes, sea level rise, and the impacts of beach renourishment projects. There have been 9 named hurricanes within a 50-mile radius of Oregon Inlet since 1980 and 17 within a 100-mile radius. Sea level rise will absolutely impact this area. I've included images from NOAA's Digital Coast dataset here at 1 foot, 4 foot, and 10 foot sea level rise, and it's pretty much underwater. Another thing to consider is that Dare County and individual towns in the county fund beach renourishment semi-regularly. This year, there are 7 towns scheduled for beach renourishment, which is essentially a process of dredging up beach-compatible material and sand from a designated borrow area and pumping it onto the beach. It's also referred to as beach widening, coastal storm risk mitigation, and sometimes even sea turtle habitat restoration. It's all a matter of semantics and funding. I really enjoyed analyzing these images in the previous slides in all kinds of ways, making predictions about my results, and then doing research to understand what was actually happening in the land use change, the land area loss, and the shoreline dynamics near Oregon Inlet. I think there's a lot of potential for future research or other ways to do this, so using more detailed imagery and larger scale information of the area, and maybe a smaller study area with on-site data collection and verification. So that's all I've got. As promised, here are my citations. Thank you guys for watching.